Alright, in this video we're going to look at a rotational kinematic sample similar to a problem that a lot of people had trouble with on problem set 7. So we have a child on a merry-go-round. The child is 2.43 meters from the center and accelerates from 0.4 radians per second to 4 pi over 3 radians per second in a time of 5.2 seconds. We want to know how far does the girl travel in meters during this time. So I have angular information. I'm looking for a linear answer. So essentially, the girl is rotating around a merry-go-round. I have a radius of 2.43 meters. I have an initial omega of 0.4 radian per second, a final omega of 4 pi over 3 radians per second, a delta t of 5.26 seconds, and that's it. What I want to find is a linear distance traveled by the girl. So really it's a two-part problem. So when we have a rotational problem that's asking for distance, we're going to use a little geometry of a circle to help us out. In one full revolution, the girl travels pi times the diameter. D and D, I'm trying to use distance and diameter without getting you confused. So pi times the diameter is 1 circumference, right, or 2 pi r equals the circumference of the circle. So for one revolution, she travels 2 pi r meters. So what I need to know is her total number of revolutions, which is a delta theta in revolutions, and multiplied by her circumference, 2 pi r, that's going to tell me my total distance traveled in meters. So the goal is using my information then to find delta theta. So what is her angular displacement during this angular acceleration? Well, I know that she has an alpha, right, because her omega is changing. She's increasing her angular velocity. So if I look at my equations for delta theta, I have delta theta is omega naught delta t plus 1/2 alpha delta t squared, or omega squared equals omega naught squared plus 2 alpha delta theta. Okay, so these are my two angular acceleration equations that have delta theta in them. So the question is, can I use either of those to find delta theta in one step? Well, first one, I need time, which I have. I need omega naught, which I have, but I need alpha. Second one, same thing. I need omega and omega naught, which I have, but I need alpha. So in both cases, I need alpha. So it makes it a two-step problem. So first, I got to find alpha. So if I know omega and omega naught in time, I know that the new omega is the initial plus the acceleration times time. So omega minus omega naught over delta t equals alpha. So I have an expression for alpha in terms of omega, omega naught, and t, which I have, which are knowns. So what I'm going to do is substitute this in and then simplify. And I'm going to choose this first equation. So this becomes my system of equations. So I will carry this out over here. Delta theta equals omega naught delta t plus 1/2. And now for alpha, I'm going to substitute in omega minus omega naught over delta t times delta t squared. And the reason I chose that one is because I have delta t in the denominator here, and I have a delta t squared. What's nice is that cancels out. So I'm left with omega naught delta t plus, and I'm going to distribute this out. So I have 1/2 delta t times omega minus 1/2 delta t times omega naught. So I have an omega naught delta t, an omega naught delta t a 1 and minus a half. So I basically have 1/2 omega delta t, this term, and then 1 minus a half minus, right? Yeah. 1/2 omega naught delta t. Oh, plus, I'm sorry, a 1 minus a half. So I have a positive 1/2 omega naught delta t. Sorry about that. Equals delta theta. So I'll simplify this. I'll pull 1/2 delta t out now, times omega plus omega naught. So this will tell me my delta theta, and I want this in revolutions. Once I get this, I'm going to go in here and then find my meters. So let's put in some values. So I have 5.26 seconds times 0.4 radians per second plus 4 pi over 3 radians per second. And the seconds are going to cancel, so I'm going to be left with radians. So 0.4 radians plus 4 pi. So plus 0.4 times 5.26 times 0.5 gives me 12.0685 radians. Now, in order to count revolutions here, so the number of revolutions times the circumference, I'm going to convert this to revolutions. So 2 pi radians per 1 revolution. So my delta theta in revolutions is 1.92 revolutions. So this goes into here, so I have 1.92 revolutions times 2 pi. My radius is 2.43 meters, and that's distance traveled per revolution. Will give me a total linear distance traveled of 29.33 meters. So again, challenges in this problem. I have a linear aspect here that I need to figure out using the circumference of the circle. I have angular information here, which is a two-part solve, two-system solve to find theta. So it's a little more complicated based on the steps, but hopefully you can see none of the steps in and of themselves are that crazy.